Hello everyone, our group is 64. This is our project on robust CN training on corrupted CIFAR. Our main goal was to improve classification accuracy under challenging conditions, specifically when the datasets contain either incorrect labels or corrupt images. We focused on two types of railroad imperfections: label loss and night version disturbance. To tackle this, we combine attention models, the data augmentation, and corruption-aware training pipeline. In the following slides, we will explain how we simulated these corporations, decided this dataset, and improved the model robustness. In real-world datasets, data is rarely clean. To simulate this, we introduced targeted corruption. First, we swapped labels between cats and dogs for 30% of their images, creating label noise. Second, we applied a light filter and flashlight glare effect to deer and frog images, mimicking low light camera footage. We also added Gaussian noise to airplane and ship images, though these were not our main focus. The examples below show how their corruptions visually alter the dataset and increase classification difficulty. This setup allowed us to test whether our model could still effectively dissipate noise inputs. This slide shows how we implement the data corruption logic. The top left code block is our corrupt labels function, which swap cat and dog labels based on a default ratio. On the right, you see two cage functions, light filter and add spotlight, which simulate night vision and glare for deer and frog images. At the bottom is our custom dataset class corruption CIFAR, which dominated applied this transformation during training. This setup lets us corrupt only certain classes while keeping the rest of the datasets unchanged, giving us full control over how each image is modified. It's efficient, modular and helped us create a controlled but realistic training environment.
In order to recover performance for corrupted classes like deer and frog, we conducted ablation experiments on several augmentation methods. The final pipeline includes four techniques: suppress overexposed, contrast only boost, color jitter, and random rotation. These were selected because they consistently improved the test accuracy while maintaining training stability. Methods like CLAHE enhancer and sharpen were excluded because they introduced artifacts or overemphasized noise. Our final selection was based on both empirical accuracy gains and the visual inspection of transformed samples. This slide shows how our augmentation pipeline works in practice. On the left is the original deer or frog image. In the center is the same image after applying night filters and spotlight simulation. On the right, we apply our domain-specific transform to recover visibility. You can clearly see that the color, vibrancy, contrast, and the structural details are much more pronounced, giving the model a better chance to recognize the object. This transform was only applied to the deer and the frog classes during training. Our model is based on a lightweight CNN backbone with three convolutional blocks. After each block, we insert a CPAM attention module. CPAM first applies channel attention to focus on important features maps, then applies spatial attention to highlight informative regions. This helps the model ignore irrelevant noise such as glare or dark patches caused by synthetic corruption. We also use SILU instead of ReLU to retain weak activations, especially under low light input. The final layers include a global average polling, dropout, and a fully connected classifier. For training, we used the Adam optimizer with a learning rate of 0.001 and weight decay. We applied the cross-entropy loss with label smoothing set to 0.1, which reduces the effect of mislabeled cat and dog images. To adaptively control learning rate, we used reduced LR on plateau, which lowers the learning rate when test accuracy stagnates. We also experimented with mix-up, specifically applied to the cat and dog classes. However, it introduced instability and domain mismatch, so we ultimately reverted to the standard loop. This combination of adaptive optimization and noise-aware loss proved more effective on our corrupted dataset.
Okay, thanks y'all. And next I will show you the currency breakdown and how our methods improve model robustness under corruption. As you can see in the bar chart, our model suffered the most on four specific classes under disturbed training: deer, frog, cat, and dog. The reason: cat and dog labels were internationally swapped 30% of the time, introduced a annotation noise, and deer and frog images were heavily distorted with night filter and glare, simulating real-world low-light conditions. So to fix this, for cat and dog, we apply label smoothing during training. It helps reduce overconfidence and improve tolerance to noise label. And for deer and frog, we designed a class-specific augmentation pipeline called deer-frog transform. This includes glare suppression, brightness recovery, and fixed contrast boost, allows the mode to sorry, allowing the model to recover thematic features even under visual degradation. Finally, we add CBAM attention models to our Pro model. This helps the network focus on key features even when the image is messy. Thanks to this change, the Pro model filter overall test accuracy to 73.6%, with significant gains in the four corruption classes. Here are the key insights from our study. The first one is robust learning needs robust data. Our experiments showed how easily CNN can break down when trained on noisy labels or visually corrupted data. This highlights the importance of addressing data inequality from the very beginning. The second, attention and class-aware augmentation is effective. By adding CBAM attention models and our customized deer frog transform pipeline, we were able to recover significant accuracy lost in the most effective classes. And the third, simple and smart beats complex. Interestingly, our model isn't deeper or larger than baseline networks. The improvements came from target, domain-specific enhancements, showing that clear design can often outperform brutal force scaling. And visually, you can think of our strategy like this: corruption and enhancement, attention, and the last is recovery. And that concludes our presentation. Thanks so much for your time and attention. And if you have any question about our augmentation choice or attention design, we'd love to chat more. Thanks again.